Chapter 4, Energy from Combustion, Part 3. We're going to look at energy changes in molecules and then apply those energy change concepts to hydrocarbons. Let's start by watching a video on measuring the energy of food. And I apologize in advance if we're still using the same video that has potentially annoying background music. The content is interesting though. So the video mentioned calorimetry, and this is a bomb calorimeter. What happens is there's an internal chamber where you can place the food and combust it, or you can place a chemical reaction, a certain mass of reactants. Basically, once it occurs, heat will be released to the water, and based on the temperature change of the water, we can actually calculate how much energy was released. And then we can describe that food item or that chemical reactant in terms of energy released in that reaction per mole or per gram. So now let's take that and look at methane in particular. So if we were to combust methane in the presence of oxygen, we would get carbon dioxide and water plus energy. That's why we burn it in our homes to heat our homes and to cook. So when energy is released in a reaction, it's called an exothermic reaction. It's exiting the reaction. Let's take a look at what this looks like on the molecular level. Here we have the balanced chemical equation for the combustion of methane. Again, we like to give you a visual view of what's happening because if you can conceptualize it, you're much more likely to understand and retain the information and apply it. So let's click on methane and see what needs to actually happen to form carbon dioxide and water. So before we start forming bonds between hydrogen and oxygen, we need to break the bonds in methane and break the bonds between the oxygen atoms. That always requires energy. Once those bonds have been broken, then the attraction between the atoms forms new bonds. And during bond formation, energy is released. Again, the remaining atoms form CO2, and when that occurs, the bond forms and energy is released. Why is energy released when bonds form? Well, you can think about if you have two objects or even two people who are very attracted to each other. If you try to keep them apart, it requires energy. So to actually allow them to come together, it's almost as if you essentially release energy because you're no longer expending that energy to keep them apart. Or you can think of it in another way, depending on your science background, that compared to the atoms being separated, them having formed bonds is a lower, more stable energy system. So the bond formation, since the energy is lower, must have released that energy into the surroundings. We want to refer to specific values when we talk about the quantity of heat energy. You can imagine in industry or in science, we need to know how much heat is given off by a reaction or things can get out of hand very quickly. This value is reported in kilojoules per mole, so thousands of kilojoules, but sometimes in kilojoules per gram. Generally, most combustion reactions are exothermic. Most favorable reactions are exothermic. Thinker buddy question. If the heat of combustion of methane is negative 50.1 kilojoules per gram, how many kilojoules are released per mole? Now think back to our chapter on converting between grams and moles to solve this problem, and use your unit analysis and write out your work as clearly as possible, and you'll have much better luck with this problem. So here's the answer. Now, if you didn't pause the video, I just want to get on my soapbox for a moment and mention that frequently there's a misconception that recognizing an answer and understanding it's a problem is done correctly is very different from actually understanding and being able to do the problem. So you might look at this, and if you didn't do the problem or pause a video, you may think, oh, I got that. I can do that. But really, you do need to practice because you might surprise yourself in an exam setting. It may be more difficult. But what this is saying, I'll get off my soapbox. For every mole of methane burned, we get 802.3 kilojoules of energy. So you can look at it also in this energy diagram. Here at the top, we have energy of reactants. You can think of it as the chemical potential energy of the bonds in methane and in oxygen. When we break those bonds and form carbon dioxide and water, these molecules have less potential energy in their bonds. If the products have lower potential energy than the reactants, that energy had to go somewhere. That's our first law of thermodynamics. It's not created or destroyed. So if the products have less potential energy in their bonds, that energy must have exited the system, been exothermic reaction. And notice the sign convention. Whenever we say a system has lost energy, or after a reaction, energy left the system, or water surrounding the reaction were to heat up, that reaction, defined as our system, lost that energy, and we use a negative sign to indicate to the person looking at that heat value, if they don't have this nice diagram, that energy was released. So whenever you see a negative sign, that's an exothermic reaction. Now the other type of reaction we haven't mentioned really is an endothermic reaction. You could think of the energy coming indoors, and that kind of works. So that's when the energy of the products is actually higher than the energy of the reactants. Say we tried to make petroleum or gasoline out of water and carbon dioxide. We would have to put a lot of energy into that in order to create these high potential, high energy containing molecules. So when that happens and you put energy into the system, we use a positive sign because you added energy to the system. It's all from the frame of reference of our system. And your frame of reference could change, but we're going to keep it simple. It will generally always be the reaction we're focusing on, or the molecules we're focusing on. Now, just one side note, a reaction may require energy and be endothermic, but it will also require a little bit of energy even if it's exothermic. The previous graph was a little bit of a simplification. You always have to put energy into a system to break bonds. It's just that after the new bonds are formed, more energy is released than was required to break the original bonds. So when we do these chemical reactions, we rearrange the atoms. We break the bonds of the reactants, we move atoms around, and we create the bonds of the products. It always takes energy to break bonds. A common mis I want to say I don't want to say misconception. It's probably more of a vocabulary uh, misuse in biology. They'll often say breaking the bond to phosphorus in ATP to form ADP releases energy. And that's incorrect. Breaking bonds always require energy. However, the products formed from the reaction of ATP to form ADP are at lower energy. Therefore, energy is released and can be utilized by the body. So, don't correct your biology teacher. They are hardworking and they're biologists. They that's not their specialty. So, breaking bonds is always endothermic. That part of a reaction. And then energy is released to form bonds. What determines if a reaction is endothermic overall or exothermic overall is how much energy is released when the new bonds are formed. Is it a little bit or is it a lot? If it's a little bit of energy, if you require energy to break bonds, and then only a little bit is released when you make bonds, then overall you will have not gained any energy or released any energy. You will have had to have a net positive flow of energy into the system. But a net exothermic, yes, you put some energy in to break the bonds and start the reaction, sometimes referred to as activation energy. But then you get a whole bunch of energy out when the new bonds form. So you're looking in the difference between the energy required to break the bonds and the energy that you get back from forming the bonds of the products. It's very straightforward. Breaking bonds needs energy. Creating bonds releases energy. Those two, always true. What varies is the net energy release. If you want to look at a little more text detailing energy changes and reactions, there's a nice website. There's also some very cool chemical demonstrations of an exothermic and endothermic reaction. Very fun, very short. I recommend them. So now let's look at different fuels, right? We've learned how to quantify energy release, put a number to it. We can use these techniques such as bomb calorimetry and look at how much water is absorbed by, or how much heat is absorbed by the water. And based on that, we can say, okay, per gram or per mole, this reaction, like methane with oxygen, releases this much heat. So we could do the same thing with pure octane. And you notice, okay, it's a little less energy. Coal, a little less energy. Ethanol, even less. Glucose, even less. So not all fuels are created equal. And that's one of the concerns with peak oil. And when people say we're addicted to oil, because hydrocarbon products and non-renewable resources like coal, octane, methane, they're extremely high energy molecules. We obtain or can harness a ton of energy when we combust those molecules. Other things, not so much. So you have to burn almost twice as much ethanol as methane. And usually they produce ethanol from somewhat energy intensive processes using cellulose or they're doing new research using algae to produce ethanol, which is a little more energy efficient, but still, it's difficult to compete with our current technology with these high energy non-renewable sources. So now let's again, energy changes are due to rearrangement of atoms of the reactants and products. We look at the net energy of breaking and forming bonds to determine if it's endo or exothermic. Now we're going to focus in on bond energy itself, the amount of energy that's absorbed to break a single chemical bond. Why is this important? Well, we know already about breaking bonds. They require a certain amount of energy. But what we can do is we can actually create averages of bond energy between atoms. And the way this table is read is between two hydrogen atoms, if there is a bond, it requires 436 kilojoules per mole of energy. Between a carbon and a hydrogen, 416. Nitrogen, hydrogen, oxygen, hydrogen, and so on. So we can create these tables of average energies for double and triple bonds as well. What this allows us to do is approximate, if we have an unknown compound, approximate the energy released when we combust that compound. Now that's a very powerful tool if you're working with, say, a newly developed explosive compound, or doing anything where you're unsure of the amount of energy released. So let's now look at a more accurate picture of a reaction. Here we have our energy diagram. We have kilojoules on the left-hand side, and we're going to just look at the reaction of hydrogen and oxygen gas forming water. Well, just like the molecular view of methane we did earlier, in order for these to form new bonds to one another, first you need to break the bonds of hydrogen. And there's, in the balanced equation, 2 molecules of hydrogen for every 1 of oxygen. So if the hydrogen-hydrogen bond is 436 kilojoules, we multiply that by 2 for each of the hydrogen bonds. Now, oxygen, if you were to do the Lewis structure, you'd realize it's a double bond. And going back to that chart, if we look at the energy to split an oxygen double bond, it's 498 kilojoules. But there's only one of them. So going from 0 up to here, around 1300 or so, that's how much energy we have to put in to start the reaction. That can be seen as the activation energy. The activation energy is almost always essentially just the energy to break all the bonds in the reactants. Once those bonds begin to form between hydrogen and oxygen, whoa, we get a bunch of energy out. And energy, the energy released from forming a bond, is equal and opposite to the energy you need to put in to break a bond. Of course, in the lab, this isn't entirely perfect, but it's true from a theoretical perspective. So if we wanted to calculate the energy released from forming those bonds, we just change the sign of the value we have on the table between the oxygen and hydrogen bonds. But this time we have H2O, so we have to form this bond between the oxygen and the hydrogen, and this bond between the oxygen and hydrogen. So that's 2 OH bonds. But then in the balanced equation, we form 2 water molecules. 2 water molecules with 2 OH bonds. That's a total of 4 OH bonds formed. So we need about 1300 kilojoules, and we release about 1800 kilojoules. So the net energy change, we end up releasing more energy than we put in. So we get 500 kilojoules of energy released. Now let's take a look at this Thinker Buddy question. Consider these single bond energy values from the table. Hydrogen bond, 436 kilojoules per mole. A carbon-hydrogen bond, 416 kilojoules per mole. A nitrogen-hydrogen bond, 391 kilojoules per mole. And an oxygen-hydrogen bond, 467 kilojoules per mole. Using those values, for which of the molecules below would the greatest total amount of energy be required to break the molecule into its component atoms? We're not forming anything, just breaking it apart. You may want to use a calculator for this. you could just guesstimate if you're good with numbers. A, methane, CH4. B, ammonia, which the formula is NH3. Or C, water, H2O. D, hydrogen gas, H2. So the answer is A, and I'll go through the calculation for each of them. CH4, in order to break those up into those bonds into the individual atoms, it would be 4 CH bonds, or 4 times 436 kilojoules per mole. That would give us a total of around 1700 kilojoules per mole. Ammonia, there are 3 NH bonds. If the average energy to break an NH bond is 391 kilojoules, 3 times 391, or roughly 3 times 400 kilojoules, is 1200 kilojoules per mole. C, water. It's just one molecule of water in this case. We're not looking at the formation of water from hydrogen and oxygen gas. Just one molecule of water has 2 OH bonds. Each OH bond is 467 kilojoules per mole, so 2 times 467, roughly 900 kilojoules per mole. And for H2, there's just one hydrogen bond between the two atoms with 436 kilojoules per mole for each bond, so that would just be 436 kilojoules per mole. This ends Chapter 4, Part 3.